Hi everyone, this is Dr. K. Kannan, faculty from ECE. Through this video, I am going to discuss about the noise characterization from Unit 3. So, the introduction to noise. Here, the following content we are going to discuss in this video lecture. First one, source of noise. Second, external noise. Third, internal noise. Fourth one, signal to noise ratio and noise figure. And the introduction, then thermal noise, and finally I conclude with chart noise. So introduction, here the noise. So noise is a general term which is used to describe the unwanted signal which affect the original signal. That is the original signal in the sense which signal we want. So these unwanted signals arise from a variety of sources which may be considered in two main categories. One is a man-made noise and another one natural noise. So the man-made noise is occurred based on the phenomenon is called interference, usually from the human source, and the second one, naturally occurring random noise. So first one, interference. So interference arises, for example, from other communication system. For example, a crosstalk between two signal, and the signal contains 50 hertz supplies and harmonics, and switch mode power supplies, thyristor circuits, ignition, that is car spark plug. So like that, so we are getting the signal by these type of external sources, so that will create the interference. That is the first one. So these interference created by human being, so that's why it is called a man-made noise. Then the introduction, natural noise. So natural noise occurring from the external noise sources include temperature disturbance. So temperature, I mean the atmosphere disturbance is electronic storms, lightning, ionospheric effect, etc. So called it is a sky noise, or it is called cosmic noise. So which includes the noise from galaxy, solar noise, and hotspot due to oxygen and water vapor resonance in the Earth's atmosphere. So the diagram shows that frequency versus noise temperature in terms of Kelvin. So first one, it's from 0.1 to 1 gigahertz where we are getting the noise is called galactic noise, and from 1 gigahertz to 10, so we have a low noise region, and 10 to 100 we have a tropospheric noise region. So where the water vapor resonance at 22.2 gigahertz, and oxygen resonance is 60 gigahertz. Then the thermal noise, the another name for thermal noise called the Johnson noise. So this type of noise is generally occurred in the resistive component like resistor, semi-resistor, and the semiconductor, and the resonance circuit. That means the real part of the impedance and the cable, etc. So the experimental result done by the scientist Johnson, that's what is called Johnson noise, and theoretical studies by Nyquist. It is he is also a scientist. So that combinedly they found the equation is V square, that is called a noise voltage. So the square of the noise voltage is square noise voltage, V square equal to 4 kTbr. So K, it is a Boltzmann constant, it is a proportionality constant, and this can be represented in terms of some value, that is joules per Kelvin, 1.38 into 10 power minus 23, and the T, it is absolute temperature, and R represents resistance in terms of ohms, and bandwidth in terms of hertz. So the equivalent, the mean square noise voltage is called V square. So V square equal to 4 kTbr. Then the law relating the noise power to the temperature and bandwidth is capital N equal to kTb. The unit of is watts. So thermal noise is often referred to as white noise because it has a uniform spectral density. So when you look into the figure where the frequency represented in the x-axis and y-axis, we are representing normally a spectral density, and the value should be constant for all the frequencies. That's why it is called white noise. So for all the frequency content, the spectral density is constant. Then the continuation, then the noise. Next one we are going to talk about chart noise. The chart noise was originally used to describe the noise due to the random movement of the electron from the cathode in a vacuum tube. For example, if you consider vacuum tube, the random movement of the electron, so that will produce some noise is called chart noise. So chart noise also occurs in semiconductor devices due to the liberation of charge carrier. Because of the liberation of the charge carrier, we are getting some noise in semiconductors, that is called chart noise. When you talk about PN junction, the mean square chart noise current IN square is equal to 2 of IDC plus 2 I0 into Q QE into B ampere square, where IDC, so IDC it is a current, and I naught it is a that is also it is a current, that is called a direct current we can have, and B represents the noise equivalent bandwidth. Here the electron charge QE represents 1.6 into 10 power minus 19 coulombs. So the chart noise is found to have a uniform spectral density as for thermal noise. So like thermal noise, the chart noise also contain uniform spectral density. Then next types, it is a flicker noise, or we can call it is a low frequency noise. So in active devices like indirect circuits, diode, transistor, etc., also exhibit low frequency noise, which is a frequency dependent. So low frequency noise means it is a frequency dependent. Frequency dependent, that means it is not uniform. Then it is called flicker noise. So the another name for flicker noise, it is 1 over F noise. Then excess resistor noise. So thermal noise in the resistor does not vary with the frequency. By means of resistor also generate a additional frequency depends upon noise is referred to as excess noise. So the noise produced by the resistor is additional frequency. So that is called excess noise. Then burst noise or popcorn noise. So some semiconductors also produce a burst or popcorn noise, which is a spectral density which is proportional to 1 by F. The spectral density of the noise is indirectly proportional to 1 by F. Then it is called burst noise or popcorn noise. Then the general comment, so based on the previous definition and all the equations, we can have the overall comment like the frequencies below kilohertz, that is a low frequency system. The flicker and the popcorn noises are the most significant, but this may be ignored at higher frequency where white noise is predominant. So when you go for high frequency, white noise will play important role. When you go for low frequency, the flicker noise and the popcorn noise will play an important role, right? From the diagram we can understand. Then how to evaluate the noise? So that is called a noise evaluation. The essence of calculations and the measurements is to be determined the signal power to the noise power ratio. That is signal power of the received signal divided by the noise power of the received signal. Can represent S by N. It is called SNR. So S represents signal power, noise represents the noise. So S by N equal to S 10 log base 10 of S by N in terms of decibel. So in terms of decibel, we can represent the ratio of signal power by noise power by 10 log base 10 of S by N. So we can represent the signal power in capital S. So that can be represented, or that can be measured by using decibel per meter, dBm. So which is equal to 10 log base 10 of signal power divided by 1 milliwatt. So that means for 1 milliwatt, what will be the signal power? That can be represented by dBm. Similarly, for noise decibel also in terms of milliwatt, we can represent 10 log base 10 of noise power in terms of milliwatt divided by 1 milliwatt. So finally, we can conclude that S by N in terms of dB equal to 10 log base 10 of S minus 10 log base 10 of capital N. So S dBm minus N dBm signal to noise ratio in terms of decibel. So this curve represents from the infinity. So from minus infinity to plus infinity, we can represent noise voltage. So at the center we have maximum, and when we go away from the center, the positive value, it is a minimum value. So it is positive and the negative side also. So this can be represented in terms of a probability. So the probability of amplitude of noise at any frequency or in any band of frequency from hertz to kilohertz is a Gaussian distribution. So from the low frequency to high frequency, then the probability of amplitude of noise can be represented in the form of Gaussian distribution. So the noise may be represented or quantified in terms of spectral density of the noise. That is called noise per spectral density P naught in terms of watts per hertz. So from which the noise power capital N is equal to P naught into Bn, where P naught is a power and Bn represents noise bandwidth. For ideal low pass filter, the bandwidth is equal to Bn, so that we can rewrite that value capital N equal to P naught into Bn. So the unit is watts. Then practical low pass filter. So 3 dB bandwidth is one, but noise does not suddenly cause at 3 dB. So therefore, always Bn is greater than 3 dB. So Bn always depends upon the actual filter what we are going to use. So in general, the equivalent noise bandwidth is always greater than 3 decibel bandwidth. So greater than 3 dB. Then analysis of the noise in communication system. So by using thermal noise, we can analysis. So look at the diagram where we have noise resistor is connected in series with voltage source Vn. So V square equal to, already we have seen 4 kTBr. The unit, it is whole square, that is mean square value and power, so that we can represent VRMS. So root mean square voltage is equal to root of V square. So when you take the root for the above equation, then you will get 2 root of KTBR. So it is equal to Vn. So Vn, it is a RMS noise voltage. So from V square we are finding Vn is a RMS noise voltage. Okay, then the system bandwidth is beta BH, and the system bandwidth in terms of what you can represent constant 2b, so K2b. So for A, now look at the diagram. For A, it is S by N is equal to S by KB. For B, the diagram B, where we are going to represent the different type of signal representation, so S by N equal to S by K2b. So system for normal and a system with some other changes. Then when you are connecting the resistor in series, then we are writing the potential equation, that is noise voltage equation for both the resistor. So if the resistor is connected in series, then we have Vn1 square, Vn2 square. So Vn1 square, it is noise voltage across resistor 1, and Vn2, it is a noise resistor across 2, so that we are going to combine. So for we can combine means what, Vn square equal to Vn1 square plus Vn2 square, where Vn1 square equal to 4k T1B R1. R1 is the resistance 1 and R2 is the second resistor. Then we are going for the comparison, combining representation, that is resistor in series, so that Vn square equal to 4k TB of R1 plus R2. See, so that when you talk about the resistor in series, then this will be acting as a single resistor. Similarly for resistance in parallel. So when we talk about parallel, it is 1 by R1 plus 1 by R2 parallel to the sources. So that the total Vn square, that is total output of noise voltage square, is equal to V01 square plus V02 square. So V01 square, it is a noise voltage across resistor 1, and V02 is equal to the noise voltage across resistors 2. Here the resistors are connected in parallel. So that final equation is Vn square equal to 4k TB of R1 R2 divided by R1 plus R2. Then we are talking about important parameter of the noise. It is called the signal to noise ratio. So signal to noise ratio is equal to the ratio of signal power to the noise power, S by N. So capital S divided by capital N equal to signal power by noise power. So we can represent this noise signal to noise in terms of decibel. So that 10 log base 10 of S by N. So S and N measured in terms of milliwatt. So look at the diagram. So signal to noise ratio at the input. So this signal to noise ratio value is given to a normal network, and we will find out what is the signal to noise ratio at the output. So input to the output. So the amount of signal to noise ratio at the input divided by the amount of signal to noise ratio or at the output, that can be represented name is called noise factor. It is capital F. So capital F equal to signal to noise ratio at the input divided by signal to noise ratio at the output. So for F, if it is equal, then we can say that it is a noiseless network. That means there won't be any noise. So if it is greater than 1 and if it is less than 1, then we have some value. So we can have the value, it is equal to 1 means it is a noiseless system. Okay, so in terms of decibel, we can represent noise figure. So when you represent noise factor in decibel, then it is called noise figure. So F of dB. So 10 log base 10 of F. So always this F value is greater than or equal to 0 dB. So the noise factor, or we can say the another name is called noise figure. It is a measure of how much a network degrades the signal to noise ratio input, and the lower value of capital F, the better the network. So it is used to represent how much the network getting degraded by the signal to noise level. So that can be represented by S by N. Okay, the noise figure, the noise factor for a active element. So consider one active element where the gain of the element is always greater than 1. Then we can find out what is the noise factor, signal to noise ratio at the input divided by signal to noise ratio at the output. So that should be multiplied by the gain. So that S, there is signal out is equal to gain into signal in. Then we can substitute this value into our general noise factor. We will get N out divided by Gn. So in general, right? So always we can say that F is greater than 1. Then the N out, that is a noise output, is increased by the noise due to the active element, because we are using one active element, right? It may be any amplifier or any device, any transistor or any diode that will be acting as a acting some element, so that is called active device. So that N out equal to Gn in plus Na. So where N in, it is a noise input, then Na, it is a noise produced by the element. So Na represents the noise getting added with the original input, it is N in. So this added noise may be referred to the input as an extra noise. That means equal. That is, extra noise means what? Some noise is added in the system itself. So NA, that should be added with the noise coming from the output side. Okay. Then we are going for the noise element. So that is G of N in plus NE. So NE, it is output is coming from some other device that is given to the element where the gain is G, and one more input is N in. So that the N out, that is noise output, is equal to gain that should be multiplied by both N in and NE. So NE is the extra noise due to active element referred to the input. The element is thus effectively noiseless. So that F equal to G of NIN plus NE divided by GN. So NE, it is a extra noise coming from the previous one, and G represents gain of that element, N represents noise input from the previous one. So that we can rearranging NE equal to F minus 1 of NN. Okay, so NN is the external noise from the source. Then TS, it is the equivalent noise temperature of the source. Then we can write NE equal to KTEBN. So T, it is the equivalent noise temperature. So finally we can get the equation T equal to F minus 1 into TS. Okay, then noise figure for noise factor for the passive element. So where we studied for the it is a active element, now we are going to talk about it as a passive element. So here the passive element we are representing in terms of some component that will not do anything, right? So it will not do anything, just it will transfer from input to output. It will not do any active purpose, right? So that it is called passive element. So for that passive element we can find out the TE. So equivalent temperature TE equal to L minus 1 into TS. Then this is a comparison of the noise factor, noise figure, noise temperature of the different devices. For example, master amplifier, gallium arsenide FET amplifier, gallium arsenide FET amplifier with different frequency, silicon transistor, then LC amplifier, then type of N cable. So the different frequency, different equivalent temperature, different noise figure, and the gain in terms of decibel. Then when you're going for the element which is connected one by one, then we can call it as a cascade network. So when you go for cascade network, then we can find out the performance based on the signal to noise ratio comparison of the input to the output. So that by using that component which is connected, for example here we have a feeder and a cable, and the second one we have RF amplifier, third one mixer, and the fourth one IF amplifier. So that we are connecting 4 element cascaded. So in that situation we can find out what is the total signal to noise ratio, S by N, at the output. So now look at that system noise figure for first system. The noise factor is F1, corresponding gain it is G1. Similarly for second one, F2 G2. Similarly for the third one, F3 G3. Right. So here the noise the systems are getting cascaded and connected to an aerial to the input, where N in is equal to NAE. Then look at that the input for one input, it is a noise input is called NAE. Then another one NE1 is equal to F1 minus 1 NN. So noise input here, noise input in the form of noise equivalent value, then NAE. Then we can sum all the things, then we are getting final equation as capital F suffix S. So system output, right? Total system output F is equal to F1 plus F2 minus 1 divided by G1, F3 minus 1 divided by G1 G2 plus F4 minus 1 divided by G1 G2 G3 plus etc. plus N. So if we go for N number of stages, so this equation is called Friis formula. That means the total noise factor for the cascaded system. So cascaded system, more than one component we are connecting serially. Then based on that we can find out the system noise temperature. Okay, thank you all. Thank you for listening this video. Thank you.